the L2 theory on the, we are doing Fourier analysis on the circle. We also did Fourier analysis on integers, which is actually somewhat sounds trivial, but the point is I will not be repeating the proofs in the case of Fourier analysis on the real line, because many of them are the same thing actually. So we will see. So Fourier analysis on R will look similar. I mean, in one sense, it looks similar to Fourier analysis on the circle group. That's the way it's usually presented. But in another way, it is actually also similar to Fourier analysis on integers because both are non-compact groups. So we'll come to that. So many theorems, I'll not be repeating the proofs. We'll go over it. Maybe I'll just go over the statements, but most of the proofs are similar. So I'll skip that. But let's continue with this. So what I was doing with Fourier analysis on the circle was we already did the L2 theory. Now we were talking about Fourier analysis of Fourier transforms of measures. And what I said there was, okay, so we have measures for which we associate a Fourier transform. Usually it's called Fourier series, okay, because it's discrete. Mu hat of n is the Fourier series, but well, I use Fourier transform. When you talk in general in terms of groups, it's always called Fourier transform. So we had three questions. Is it injective? Because on L2, we know that L2 of T, L2 of circle group corresponds to L2 of the integer. So there is a bijective correspondence, which is in fact an isometry. Whereas on measures, first of all, what are the functions which arise as Fourier transforms of measures? That is written here in question 2. And is it injective? I mean, can two measures have the same Fourier transform? And what properties of measures are encoded in the Fourier transform? Okay. And you can ask identical questions for L1 functions. Now, the fact is for measures, we saw that it is actually injective. Okay, so this is injective because, well, we did that proof. We defined convolution. Basic idea was to convolve mu with a smooth, nice function. We took the fair kernel. It's not necessary. We could do many things, but we took the fair kernel and convolved mu with that and got a function. And this function has this form. This function is entirely expressed in terms of mu hat, and it converges, or if you look at the measure with this density, that converges to mu. We said it in a precise sense that integral of Fn over an interval, over an arc, converges to not exactly mu of that arc, but mu of the open arc plus half of the endpoints. So what we saw is that here. So this thing converges to mu of the open arc plus half of mu at the endpoint. So if the endpoints are not atoms of mu, then you get mu of the arc. And the right side is expressed entirely in terms of the Fourier transform of mu. Therefore, you can recover mu from mu hat, and it even gives a kind of vague prescription. Okay, so this is what I did. And okay, I did also a corollary that in the special case, when if mu is a measure, mu hat is here. So one of the things is mu. If mu hat is in L1, then you have a more simple expression for the inversion formula. Okay, so you can write. Actually, this is not quite mu hat of minus t. That is what that will be your density. Okay, so mu hat of n e to the int. That's how you recover, right? I mean, f hat n for L2 functions, this is how you would recover. F hat n was f in a product with e to the int. So if you want to recover f from that, you do f hat of n e to the int. So similar thing here, that the density of the measure can be recovered like this. So the claim is that if mu is a measure where mu hat is in L1, then mu does have a density which is in fact bounded, and it is given by this. And we also finished the proof of this. We started with the inversion formula here and just took a limit to get applying dct. Okay, but this theme I will come. I want to emphasize. So the point is, well, okay, it's an extension of the previous one. It extends the, but it is what it is the following type of thing. It is a very general point about Fourier analysis. Okay, so let me just say so little bit about the language here. See, so if you have a function, so just the so suppose f is a function on let's say L1 of t. Okay, so just so it can be nicer than that. So we think of it as a function on minus pi to pi or 0 to 2 pi, whatever you like. It is some function. I am drawing here a continuous function. Okay. Then what are f hat? The product en in L2 of t. I shouldn't write that because it's an L1 function. So let me just write the formula. Is the integral on minus pi to pi of f of t e to the minus int dt over 2 pi. So this is, so e to the int, if you look at e to the int with, well, basically you should think of the two parts, cos nt plus I sin nt. So you can draw the real and imaginary part. So the cos nt will look like something, I don't know. It is some oscillatory thing, and sine will look something similar. So maybe it will go like this. Okay. Etc. Okay, cos and sine. So what this is, what the Fourier transform, the Fourier coefficient is the amount of frequency n in the function f. Okay, so this one we'll think of as frequency n. Okay, cos nt has frequency n, or if you want it is n over 2 pi, whatever, but let's call it frequency n. So this is in some sense how much of that frequency is needed to make up the function. Okay. So in some sense, so the recovery is that the recovery formula when it works. F hat of n e to the int, this one, this is of course in L2 sense, but it can be true in better senses sometimes if the function is nicer. But this is decomposing f into these cosines and sines. Right, so and how much of a particular frequency is there, that is what I say, that's the amount of frequency, this n frequency in f. So this is the language which electrical engineers use, and it's very useful and to think that way, that the Fourier transform, it measures the frequency. So it has, that gives a lot of idea. So what, for example, I didn't actually compute a single example, but let's take for example f is constant 1. Okay, so then what is f hat of n? It is e to the minus int dt over 2 pi, which is 0 if n is not equal to 0 and 1 if n equal to 0. That is the 0 frequency. This is in fact the 0 frequency function which is there, and you don't need anything else to build that function. So that's an example, a very trivial example. And if you take a finite linear combination of sine nt, cos nt's, then you will get only finitely many of these. You will get back the actual function. But the point is that, so this, the more generally, if your function looks like this, if a function is somewhat flat, okay, and let's take another function which is wildly oscillating. Okay, so take two functions. One is somewhat stable. The other one is just highly oscillatory. Okay, so let's say this is g and this is f. Okay, so what would you think of the Fourier coefficients of f and g? Okay, see, if you look at the fundamental functions cos nt and sin nt, what happens when n increases? So when n increases, so for the lowest one, it will be like this. If you increase the n, it will oscillate more often. Okay, so if something has to very quickly Okay, if a function has to vary quickly, then it has to use higher frequencies. If you only use low frequencies, you cannot oscillate very fast, right? It's kind of intuitive to feel that. So what we'll see is that if G will have, I mean, even if F, okay, so that we have to normalize in some way. Let's assume F and G have the same L2 norm. So F hat and G hat have the same L2 norm in Z. So F hat of n squared sum is same as G hat of n squared for simplicity. So G hat puts more weight on high frequencies than F hat. It has to, because F is kind of slowly changing, so it doesn't need high frequencies to do the slow changes. Small frequencies will take care. But for rapid oscillation, you do need high frequencies. So G hat must use high frequencies. Okay. Is that clear, or any questions or anything like that? Okay, if not, so going further, what that means is that if you take in what is highly oscillatory, an extreme case of that is that function is not smooth. Okay, so highly oscillatory means the derivative, I mean, not differentiable means derivative blows up, right? So, so in particular, what this suggests is if f is not smooth, or the less smooth f is, the higher, the more it puts weight on larger frequencies. High frequencies. High frequencies means mod n large. Okay, so n and negative n, they basically are the same frequency. You have to use both to get cos nt and sin nt. So when I say large, I mean mod n is large, absolute value n is large. So this is a theme that we see by just looking at this. Okay, so one of the, let me just give an exercise here, very simple one. So one small exercise is that if f is in C1 of t, show that f dash, then f dash is a continuous function, right? So you can, and it's particular, it's L1. So f dash hat of n is actually f dash hat of n is, I don't know, plus or minus in f hat of n. Okay. So the Fourier coefficients of the derivative are basically n times the Fourier coefficients of f itself. Okay, so this is a plus or minus I have written because, okay, I don't want to figure it out. You figure it out. Right? Yeah. But so the point is, if you think in the worst case where f dash is, so if f dash is not even if f dash is not an L1 function, suppose f was not C1, f dash was not even an L1 function, then the Fourier coefficients will, for example, I mean, it's not even L2 function, let's say, then this will not be square summable. That means summation n square f hat n square will not be square summable, because like that. So it's kind of the same thing said in another way, that the less smooth f is, the more f hat puts weight on higher frequencies. Okay. So this is the idea. Okay, so this is what, I mean, this is actually the theme of this also. Here I have stated for measures, but if mu hat, so it's said in a contrapositive way that if mu hat has to not put weight on high frequencies, that there are many ways to characterize that. What do you mean by it doesn't put? So one way of saying it, so let me just summarize this discussion here, that so in general, so decay of mu hat or f hat is closely tied to smoothness of mu or f. This is a running theme throughout Fourier analysis. Decay of the Fourier transform corresponds to smoothness of the measure. Smoothness of measure means first it should have density, then the density is continuous, then it is differentiable, then it's smooth, etc. Okay. So decay of the Fourier side on the Fourier side is corresponds to smoothness on the measure function side. So this is something one has to get used to. The way Fourier transform encodes properties of a function is non-trivial. In fact, many things are non-trivial about it, but some are transferable. In particular, the smoothness versus decay. Even the other side would be true, by the way, but it doesn't make sense here. So let me just write it. Smoothness of mu hat or f hat corresponds to decay of mu or f. Actually, this does not make sense for the circle group. Because from the circle group is compact. What do you mean by decay of a function? There is nothing to decay. You have to have infinite space for a decay. Correspondingly, the dual is integers. What does the smoothness of a function on integers means? It means nothing. Okay, so it does not make sense for that, but it does. But it is, as a general theme, you can keep it in mind. It does make sense for if you are interested in the group Z and its Fourier coefficients, Fourier its dual, which is t. If you are on the additive group of integers, then you can talk about the decay of a function. Okay, I mean how fast a function decays on integers on plus infinity, at plus infinity, and minus infinity. And since z hat is t, you can talk about the smoothness of the Fourier transform, etc. So that makes sense. But of course, here this does not make sense. Because same problem. I mean, if you have a function on integers, there is no question of smoothness and there is no question of decay of the Fourier transform. So it doesn't make sense. When we go to real numbers, I mean the group of additive group of real numbers, then both R and R hat will be R itself. Then both these statements are true and will be interesting. So decay on one side will correspond to smoothness on other side and vice versa. But in compact case, decay doesn't make sense. So that's something to keep in mind. Okay. So this is the general theme. One thing you should remember about Fourier transforms. And many of the theorems are to that effect. So this corollary, which I just stated last time, is basically one such theorem. It says that if mu has a Fourier transform which decays, okay, it has a decay, because we are saying it's in L1. We could say decay in many ways. We could say it decays so fast, give a bound on how fast it goes to 0, but we are saying it is L1. It's a way of saying it is summable. I mean, it's summable means it's a way of saying it has to decay fast. Then mu will be smooth in the following sense, that it has a bounded density which has an explicit formula. Okay. And now another thing I had stated, this is like, I don't know whose lemma it is. In R, it is called Riemann-Lebesgue lemma. So it is Riemann-Lebesgue like lemma, which some of you may have seen. If mu is a measure that has density, then it goes the converse way. So, okay, so here we got from decay of mu hat, we got smoothness of mu. Here we take smoothness of mu and get decay of mu hat, but it's not an exact converse. It's not an exact converse, as we will, as you see that it doesn't say mu hat is summable. It is, in fact, if it was summable, it would have to have bounded density. But even assuming bounded density will not tell you that mu hat is summable. That's not an if and only if statement. So there is a decay. Okay, there will be a loss if you go and come back by these two lemmas. So let's prove this one. Any questions, comments before that? Okay. Okay, so let's prove that the theorem. So if mu is a finite Boyle measure on the circle group, has a density, then mu hat of n converges to 0 as n goes to plus or minus infinity. Okay, so that's the statement. Now, how do we prove it? Okay, how do we prove it? So, well, the point is there are a couple of ways. So it's a direct, I mean, so it has a density. Density means, so let F be the density. Actually, I could state a more general theorem. Maybe I should say that. So maybe I state it more generally. Did I state it that way there? I stated it that way, but in fact, let me state a more general statement. In fact, if f is an L1 of t function, then f hat of n goes to 0 as n goes to plus minus infinity. So densities of measures are always L1 functions, of course, but they have the additional property of being positive. What the second statement is saying is that that's irrelevant. So you take any L1 function. So this implies the first one. That is kind of clear, right? So this is first statement follows from the second. So let's work with F1. As always in analysis, these spaces, we only know them kind of, I mean, in a sort of, I mean, in some sense, what is L1? I mean, it is a completion of something. So you oftentimes, most often you won't be able to work with them directly. You have to work by approximation. So here you have a choice of approximations. You could approximate, there are two good ways of approximating in analysis. One is approximating by simple functions or step functions, simple functions. Another is approximating by smooth functions. So let me do approximation by smooth functions. So I fix some epsilon positive and find a g such that C, I mean, what I mean is C1 of t is dense in L1 of t. Okay, it's an easy thing. Uh, you can think why this is true. It follows from something we have already done. So C1 function, you can approximate f by C1 functions. By the way, there is a rain here and it's quite noisy. I am not quite able to hear myself. Can you hear me?
Yes.
It's not noisy? Okay. 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 So first we approximate f by an L1 C1 of t function. So it is pretty close. So what would that say? Then since the L1 is like this, so if you look at f hat of n minus g hat of n, that is just the integral of f of t minus g of t e to the minus I mean, okay, without the absolute value. So f hat of n minus g hat of n is the integral of this against which is less than equal to the L1 norm of f minus g, which is less than epsilon. Okay, so that is f hat minus g hat L infinity norm on z is bounded by epsilon. That's what we get. So it's so what okay, so I'll come to that. So how is that useful? Now let's look at g hat. What happens to g hat? g hat of n, which is integral minus 0 to 2 pi, whatever you want to write. It's a C1 function, so it's continuous even including endpoints. G of t e to the minus I n t dt over 2 pi, which is, if you do integration by parts, okay, so g has a derivative, right? So let's write it like this: g of t e to the minus I n t. This is also smooth, of course. Minus I n 0 to 2 pi minus g dash of t e to the minus I n t divided by minus I n. So this becomes a plus 1 over I n dt. Just integrate by parts. If you integrate by parts, then this is, and this is 0. This is 0. And this is 1 over I n g dash hat of n. Actually, I solved the exercise for you. If g is C1, g hat of n is 1 over I n g dash hat. G dash hat is I n g hat of n. Okay. So but we know that hence g hat of n is less than equal to 1 over n mod n times g dash hat of n. But just like we showed, L infinity norm is bounded by L1 norm. So this is bounded by L1 norm of G. Sorry, L1 norm of G dash divided by absolute value of n. And of course, that is big O of 1 over n as n goes to plus minus infinity. So G hat n does decay, and not only does it decay, we can even give a rate of decay. It decays like 1 by n. It decays like 1 by n. And now you get that from here. So using star, so g hat n goes to 0. So what happens to f hat n? Lim sup of f hat of n, let's say absolute f hat of n is less than epsilon actually, because g hat n goes to 0. This goes to 0. F hat n minus g hat n is bounded by epsilon always. So lim sup of f hat n, I mean absolute f hat n must ultimately lie in minus epsilon to epsilon. So this is true, and true for all epsilon implies f hat of n goes to 0 as n goes to plus minus infinity. So try to think why, if you can prove this without this approximation step. It's not easy. You can do a different approximation. Maybe I leave it as exercise. Give another proof using approximation by step functions. If you have seen measure theory, you may worry, do I mean simple functions or step functions? I mean step functions. Step functions are not always good enough to approximate, but in L1 it is okay. All right. I mean, so what we see in measure theory class is that simple functions are what we use to approximate, right? But for L1, we can approximate also by step functions, just like with C1 functions. Okay. So you can do another proof like that. Anyway, the whole gist of the proof is the following. Okay, so the intuition behind the proof was the following: that if f is L1, so let's say it's approximate, or if it's a smooth function or something, so it's approximately flat. So the reason why f hat of n goes to 0, another, just to think properly, is that if you break it into small intervals and you are integrating, its f is approximately like a piecewise constant function. Okay, so you can think of it like a piecewise constant function, and you are approximating a very high frequency function against that. So that almost cancels, right? So if you integrate sine nt on a small interval, you get some approximately 0 when n is large. You get 1 by n like answer. So that's why so if f is approximately piecewise constant, then you get that, and you can do a proof by approximation. Anyway, so that's the end of this proof. So this is a useful. So these two lemmas are actually useful sometimes. It's not a. It doesn't say when mu. If you want to know when mu a measure has density, these don't give a characterization, but it gives. This one gives a sufficient condition for to show that mu has density. Actually, it can be tricky to show a measure has density. So if you can analyze the Fourier transform and show that it is in L1, then you can show it has density. On the other hand, if your Fourier transform does not even converge to 0, then you know that it cannot have density. Okay, so these two give some, but there is a window in between the two where these two lemmas give you no conclusion. We will see an application of this to a very interesting problem later. We'll see an application of this type of thing, but on the real line. Okay, I will do it in the after I do the real line, I will do an application. Any questions, comments? Okay, so in the notes there are exercises to the effect that so there are exercises which go further in this business. So assume that so like this extensions of this would be that assume that mu hat decays much faster. Assume that suppose n times mu hat of n is summable, or n to the 10 times mu hat of n is summable. Then what can you say about the mu? It will have density which will be so many times differentiable. And analog of this lemma, further going along the lines of this lemma, is you assume mu has a density which decays, not just goes to, I mean, sorry, mu has a smooth density, maybe 10 times differentiable. Then can you say more about the decay of mu hat? Yes, you can. Okay. So that finishes this topic. So of the questions I stated, so we have kind of done this and done a little bit of this. Incidentally, yeah, okay. So now what is the range of this? Question 2. I will just mention, it's a very interesting theorem, but I will not prove it. So now answer to question 2. What are the functions on Z that arise as mu hat for some measure mu? Okay. So it's not that every function. So functions on Z, not every function. So note that here is the why not every function. Okay. So there are some measures. So it's a general theme, by the way. There are hundreds of theorems, or not hundreds, I don't know, many theorems of this to this effect. Usually, I mean, the historically developed like that. Many theorems were proved, and later there is a theorem that you, but the one that you see in today's analysis class is usually what is called Rie's representation theorem, which says that if you have a positive linear functional on the space of compactly supported continuous functions on the real line, then it must be integration with respect to a measure. So there are many theorems to that effect. So if I give you a sequence of numbers, are they the moments of a measure? Here we have a similar question. It's not moments. I give you a sequence of numbers, namely a function on integers, doubly infinite sequence of. Then is it the measure? Is it the Fourier transform of a measure? Now, always on the measure side, the measure is not just any arbitrary thing. It has the positivity condition. So the question is always how does this positivity condition transfer? And the answer is almost always like this: that you're given something, you're given a function. Okay, let me write rather than talk in abstract. Let me get a necessary condition and then explain. Okay, so that a necessary condition. Suppose mu is in M of t and consider mu hat. Okay, so what is a condition? So what this tells you, these are integrals of these things, right? So let's look at something like this. Ck e to the ikt. Not even if you want it need not be k. I mean, it doesn't matter much, but imkt. K equals 1 up to n. So consider something like this. Okay, and take its absolute square. So it's a positive function, right? It's a positive function. So ck's are some numbers and mk's are some integers. So if you integrate it against the measure, you should get zero, no, something that is non-negative. That's how positivity of measures always shows that positive functions should have positive integrals. That's what measure does. Okay, that's what positivity of measure is. So this should be true. On the other hand, this you can expand and interchange with the, I mean, this is a finite sum, so there is no need to justify anything. So if you expand, you get ck cl bar, and then you will get the integral of e to the imkt minus imlt. So e to the imk minus mlt d mu of t, but which is nothing but ck cl bar mu hat of mk minus ml. So these conditions have to be, so if I give you some function, okay, and so this must be true for all n greater than or equal to 1, for all m1, m2, mn integers, and for all c1 up to cn in complex. Okay, so this is how it works. So ckcl bar mu hat of mk minus mn. Then
Where is L in that? I'm sorry. Like k equal to 1 to n. Is it or
k and l, it's a double sum actually. Sorry. Yeah, thanks. So it is actually a double sum. Both k and l run from 1 up to n. So this condition has to be satisfied. So not every function will satisfy this. So for example, so just as a very simple example, you just take n equals 2 and m1 is 0 and m2 equal to 1. What does this say? This says that mu hat of 0, it comes 2 times. Okay. Well, what it says is basically that, so here you have well, okay, let me first write this. What is this? This condition is actually, it is positive definiteness of a matrix. So you look at this infinite matrix. So this is a doubly infinite matrix. On the diagonals, you have mu hat of 0, mu hat of 0, and so on. On the next one, you have mu hat of 1, mu hat of 1, and so on. And below, you have mu hat of -1, mu hat of -1, and so on. Okay, so it's an infinite matrix. It's a what is called a Toplite structure. On the diagonal, you have mu hat of 0. Next diagonal, all entries are mu hat of 1. Next diagonal, all entries are mu hat of 2. So if you look at a single row, that is just mu hat written out as a sequence. And then you slide it along to the left and right to fill up all the other rows. So what this is saying is that this matrix, these conditions are just saying that this matrix is positive semi-definite. Okay, meaning that all, what does infinite matrix being positive definite mean? All finite principal submatrices are positive semi-definite. Okay, so for example, if you take mu hat of 1, mu hat of 1, mu hat of minus 1, mu hat of 0. Okay, by the way, this is a Hermitian matrix because mu hat of minus n is mu hat of n bar. It's not always true that f hat of minus n is f hat of n bar. If it's real valued, then it is. So in this case, it's a measure, a positive measure. So it is true. So this is actually a Hermitian matrix. So what? So this has to be positive semi-definite. So in the sense of PSD. So for example, mu hat of 0 squared is greater than equal to mu hat of 1 squared. So this is one example of an inequality here. So that has to be satisfied because determinant has to be non-negative. So mu hat of 0, mu hat of 1 can't be larger than mu hat of 0. In fact, you see mu hat of 0 has to be the largest one in absolute value. Nothing else is larger. So that is one condition, but all the conditions, I mean, these are many conditions we have. So this is, so we just say, so here is a definition. A function phi from z to complex numbers is said to be positive definite if, firstly, phi of n is phi of minus n conjugate, it should have that property, and the matrix where you put phi. So let me just write phi of j minus k, jk in integers. So the j comma k entry is phi of j minus k. This is same as writing this infinite matrix, the Toeplitz structure. So is positive semi-definite. Okay, so that's what positive definite function is. And the theorem, this is the theorem of Herglotz. So remember, what we are trying to answer is what are the functions which arise as Fourier transforms of measures. We found that it can't be any arbitrary function. It has to have certain inequalities, satisfy certain inequalities. Herglotz theorem says that nothing else is needed. If phi from z to c is positive definite, then phi equal to mu hat for some Borel measure on the circle. Okay, the other way is already proved. So this is an if and only if statement, but the other way I have already shown. If mu is a measure, mu hat is positive definite. What we are now saying is that every positive definite function is actually mu hat. So this is a theorem which goes fully general to the level of locally compact abelian groups, which I will mention. But I will not prove it. We have proved the easy part, the hard part we have not proved. Okay, so it's just useful to know it. Any questions, comments here about this so far? It's not an easy theorem, by the way. You need to do some work to prove it. It's not trivial. You have to generate the measure out of a function, right? So, well, in some sense, you have to. Well, one way of doing it is somehow mu hat. If phi is mu hat, somehow mu has to be recovered from mu hat by Fourier inversion. But the Fourier inversion is not necessarily a straightforward thing. That has a limit and all that. So somehow using phi, what you do is you define a linear functional on continuous functions on the circle and show that that is a positive linear functional and use this representation to conclude it. That's one way. Anyway, so I will not be proving this. But are there any questions, comments, etc.? If not, I will go forward. Maybe I will just, yeah, I have a few minutes. So, by the way, I mean, something I began asking once, but then forgot. So, how many of you are very familiar already with at this level? For example, Fourier analysis on the circle. How many of you were unfamiliar with some parts of it at least, or substantial parts of what I said? Or so, can you please raise hands if you? Okay, so many of you, it looks like, had already seen. There are a couple of people who had not seen. Okay, so and what about on the real line? What about Fourier analysis on the real line? How many of you so think that I mean, so you are not too familiar with it? Again, about at the same level, just doing the basics. Okay, so my question now is the following. So whether I can, my plan was to do like this, that now my plan was like this, to state Fourier analysis on the real line, just state everything, and then go over and but not really prove things, because most of the proofs are similar to the circle group. Maybe indicate one or two things here or there, but that's all. But just state everything for the real line, and then also just tell you the story for the locally compact abelian group case. Now so depending on how people feel, I can just state the general theory for the locally compact abelian case and think of real line as a special case. I mean, is that also okay, or is it preferable if I do the real line? We will only use the real line situation actually. So is there any preference between this?
The real line may be better, slower path.
Okay, so then I will just do the Fourier analysis on the real line, and then I mean, do means mostly state things. Even for locally compact abelian case, it will be stating things. So let me see what I should do now. Okay, maybe I will just tell you the story of the locally compact abelian case, which is completely optional. Next next lecture, I will do the real line case separately and write out all the theorems and so on. Okay, I mean, just a reversal of order, which probably will not be too problematic. Is that okay? I will do the real line case, but I will do it next time. So I will just mention the locally compact abelian case now, because that will clarify some things. And then, but it's entirely optional, as I said. We will not be having any real applications with that.
So I have one question regarding the Havelock's theorem. So you mentioned that it will be true for general locally compact abelian group or compact abelian groups?
No, locally, I mean, so it will be, so when you, there will be what is called a dual group, and it is true, you will need a continuity condition extra, that's all. If, for example, okay, so here itself, you can ask, so what functions, so just to answer your question, what functions psi from T to complex numbers are Fourier transform of measures on Z. Okay. I mean, so measures means I mean finite measures. Otherwise, I cannot define Fourier transform. So if you ask, it's a very similar type of question. Okay, so what is a measure? So mu is a measure, finite measure on Z, suppose. So then mu is summation some an delta n in integers, right? Where an's are non-negative and summation an is finite because it has to be a finite measure. So again, you have the positive definiteness. Then you notice two things. One is you can form the same thing again. So you look at mu hat of Cj Ck j comma k equals 1 up to n Cj Ck mu hat. Now we are looking at Tj minus Tk. So is greater than Cj Ck bar greater than equal to 0 for all n greater than equal to 1 for all T1 up to Tk in the circle for all C1 up to Cn complex numbers. Okay, so this I will leave as exercise. So do exactly like I did above. You will see that you try to write this as the integral with respect to this measure of some positive function. It's more or less identical proof. Okay, so this is true. But there is one more additional condition, namely that mu hat is a continuous function. We have seen this because it's a I think I mentioned this. Mu hat is necessarily a continuous function. So why? I mean, so let's look at mu hat of t is sum over n an e to the int, right? Over n in integers or minus int. So this is a continuous function of t. Why? If an is summable, if tk converges to t, use dct. Right? If tk converges to t, then some ends converge. E to the minus int k converges to e to the minus int. So if you can use dct, you will conclude that mu hat tk converges to mu hat t. So these two conditions are there. And this way, so when I was loosely speaking, the converse will, the full statement says that phi will be mu hat. So for example, a function, so the theorem is the theorem which in general we will state for as called Bochner's theorem, is that psi from t to, I mean, in this special case is Fourier transform of a measure if and only if. Okay, so one more point here as part of this, if and only if psi is continuous, and so one thing that I have not written here is psi of t is psi of minus t conjugate and summation Cj Ck psi of Tj minus Tk greater than equal to 0. Well, for all Cjs, for all Tjs, and so on. So this is the form in which it is true. When I stated in Z, there is no point in saying phi is continuous. Every function on Z is continuous, but that is one extra bit that will be there. Okay, so did that answer your question, Shubhajit, right?
Yes, yes.
So that's the one bit that one has to add. Okay. Yeah. Okay. So yeah. Anyway, now yeah, I'm almost out of time. So let me see if there is something that I missed which I should tell. So maybe next time then I will start with the real line itself rather than with the look. Well, one can do both ways. Let me figure out. Okay, I will do it afterwards. Yeah, is there something that I wanted to say which I have left out? Okay, maybe I can give as exercise some. You can, so maybe I will put this also as exercises. Uncertainty principles also can be, since I spent time doing it in the discrete case, let me not do it here, but one can easily do uncertainty principles here. So let's look at, for example, suppose f is in L1 of t implies f hat is in L infinity of z, and we know that f hat L infinity z is less than equal to f L1 of t, right? So this we know. Now, what is it that we wanted to do there? Yeah, what was the basic uncertainty principle? We had this, and we also have what is it that I wanted to do?
I think the discrete case we did the ratio of those norms, right? The L infinity, L1 norms for both of them. So in this case, maybe
Okay. So
you have to be a bit careful.
So if also f hat belongs to L1 of z. Okay, suppose that is not guaranteed. In finite case, we didn't have to state this if conditions. Yeah, thanks, Kaushik. Yeah, now I reminded. If f hat also is in L1 of z, then f hat belongs to L infinity of t, because the other way is also true, and this is more or less so f hat. Okay, f hat in L infinity of t is less than equal to f hat in L1 of z. Okay, but this is f hat is basically f of minus t, so this is actually same as L infinity norm of
It's
f.
1 o'clock.
Okay, I will end in a minute. Okay, so this is same as this. So if you take these two inequalities, what we get is you just divide and multiply so you divide both sides and multiply f by its L infinity norm times f hat, here it is in L1 of z, by f hat in L infinity of z is greater than equal to 1. So it is a basic uncertainty principle. Okay, so can you get an analog of, so let me leave that. Donohoe-Stark. What is the analog of Donohoe-Stark? This is for L1 and L infinity norms, but there you have to talk about the supports, right? Of course, talking about finite support doesn't make sense. It may make sense on Z side, but not on T. So what is the statement of Donohoe-Stark that you can try to get from here? Maybe I will stop there. Okay, so I'll stop recording.